Okay. Size of the microprocessor. What is the size of the microprocessor? What we call it a size of microprocessor. The size of the microprocessor is nothing but a data size it can handle. So how you decide the data size? In terms of bits. A data can be 8 bits, it can be 16 bits, or it can be 32 bits, or 64 bits. That is called as size of the microprocessor, right? So how do you decide this microprocessor is of 16-bit microprocessor? How do you decide this microprocessor is of 32-bit microprocessor? How do you decide? By looking at the specifications of any microprocessor. These are the three things. What are those? Size of the data bus, size of the registers, and size of the ALU. Suppose if I say your ALU is of 32-bit. Suppose if you say your registers are 32-bit. Suppose I say your data bus is 32-bit. All these three are normally same for microprocessor. Size of the data bus, size of the ALU, and size of the registers normally remains same for a particular microprocessor. Whatever be the size of the register it has, same size ALU operation it can do. If the register size is say 16 bits, corresponding microprocessor will have 16-bit ALU. Okay? And similarly, it will have 16-bit data bus. I have informed you already what is a data bus, right? Data bus carries data. Address bus carries address. So when I have to do 16-bit arithmetic and logic operation, I have to bring in 16-bit data, right? So I need a data bus or number of data lines which has to be 16. Hope you are able to understand this, okay? So question here that how do you decide the size of a microprocessor? There is nothing but either you can say size of an ALU, size of a register, or size of a data bus. That will tell you that, okay? So now when you study this microprocessor, this is something which you need to know, okay? May not be great from learning from examination point of view, or okay. See, this microprocessor can be studied, viewed in three different angles, three different ways. Okay. One is instruction set architecture. This is what we are going to see now. We are going to see this instruction set architecture. Every microprocessor, listen carefully, every microprocessor has its own instruction set, right? I told you about instruction in my previous class, okay? Instructions are used for programming, okay? Those programs are written either in assembly level language or in the high level language. It depends on the whatever programming language you choose. But every microprocessor or microcontrollers, whatever you use in your mobile phones, comes with the instructions. So based on the instruction set it has, that microprocessors can be studied. Suppose if you are a programmer, okay, if your aim or study objective is only to program a microprocessor, you need to know about its instruction set architecture. Enough, that's enough. You need not know what is the adder circuit it has, right? What is the logic circuit it has. You need not know. because you are just going to program the microprocessor. You need to know from my instruction set point of view, how does it look like, right? Suppose if you are a designer, if you are a hardware, pure hardware designer, right, you are going to design a hardware, you are going to interface peripherals, you are going to interface sensors, you are going to interface monitors and all those things. At that time, you need to know about microarchitectures. Microarchitecture is something from where you study a microprocessor by looking at its connections, hardware connections. How does your ALU connected? How many registers are there? Which flip-flop you have used? Have you understood? Right? So by keeping the hardware design point of view, okay, if you study a microprocessor, that is called as microarchitecture. There you are supposed to know which flip-flop you have used, which ALU you have used, right? What is the logic circuit behind that? Everything you are supposed to know when you study a microprocessor from a microarchitecture. Next, one level down, that is physical realization. Physical realization is not at all for computer science graduates, not at all. It's only for electrical engineers because they study something called microelectronics. They design ALU using transistors. The study of your microprocessor in a transistor level is called as physical realization. A microprocessor can be studied in three different levels. One is only instruction set architecture. This is for computer science people. Only programming. You need to know instruction set architecture of the microprocessor, that is enough. Right? Because you do only programming, nothing else. Right? Suppose if you want to design a hardware, you are a hardware plus software engineer, suppose. We call it the firmware. Then you need to know both instruction set architecture and microarchitecture. What does the microarchitecture says? Microarchitecture, you study, about the connections, interconnections, hardware, all the hardware part, internal connections. How does ALU is connected to your registers? How registers are designed? That's where you do microarchitecture. Then one more level, still go down. How does these gates which are used in the registers, how does these flip-flops which are used in the registers are designed using transistors? That is called as physical realization. This can be done only by VLSI engineers. This person who is working with the microprocessor in this level, okay, will not bother about other things. He will just design a circuit. Okay, he will just think of how do I reduce my size of the transistor, how do I increase the speed of the processing by making transistor sizing, right? Okay, so these are the different level of abstractions you use when you study a microprocessor. Now, in this course, what are we going to do? Right? In this course, we are going to see these two, instruction set architecture. You are also going to see microarchitecture, but more emphasis on instruction set architecture. We are more emphasizing on the programming microprocessor. Then we never touch this. We never touch this. This we just see how it exists. That's all. We're not going to design anything. You're going to design memory interface that comes in the second half, okay? But initially you're going to give more emphasis on the instruction set architecture, okay? So instruction set architecture. Now, there is something to do for this instruction set architecture. So what is important for us here is instruction, from where your programming starts. Okay. A computer, I'll come back to this later, okay. A processor, you try to understand this concept, this is very important. A processor can be designed by keeping its instruction in our design criteria, okay, by keeping instructions in our design criteria. What is this? See, you have a processor. How do you make your programming easier? You have a microprocessor. When you have a microprocessor, when you design a microprocessor, you have to program it. It's not a showpiece, you have to program it, right? Is it not that you have to make your life easy while designing its instructions? Yes or no? Right? The company X also designed a microprocessor, say Intel. Similarly, the company Y, which is Motorola, also designed a microprocessor. Both are microprocessors only, competitors. The world is highly competitive nowadays, right? Both are microprocessors only, right? Everything is same. Speed, it's a 16-bit, both are 16-bit. But the instructions set of one microprocessor makes your programming life easier, and other instruction sets makes your programming life little tougher. Which one you prefer to buy? The one which makes your programming life easier, right? Yes or no? Which makes your programming life easier. Have you understood this? Okay? That means a microprocessor can be categorized based on its instruction set. That means based on the instruction set. Your instruction set can be easy or it cannot be easy. It's a possibility. There are two processors. One processor, you have your instruction set is easy. Maybe another processor, instruction set is tough, but it is faster. Instruction set is tough, but it is faster. So people can choose this microprocessor based on the requirement. Suppose somebody wants to use their microprocessor for real-time operations. Even though instruction set is tough, doesn't matter for them. Speed matters, right? Suppose microprocessor is used for non-real-time application, okay? Non-real-time application. For them, speed is not a matter, but programming easiness matters a lot. They will buy a processor which gives them a easiness in programming. Have you understood this? This is where you classify your microprocessor based on the instruction set architecture. That is what this CISC and RISC. CISC is complex instruction set computing, reduced instruction set computing. Complex instruction set computing, reduced instruction set computing. What is this? These processors itself are called as CISC processor and RISC processor. Okay? In simple way, I can tell you an example which is there with you only now. The processors which you use in your laptop, all Intel processors, or we say x86 processor, are all CISC processor. I will tell you why it is CISC processor. Clearly try to understand the difference between this. I'll try to explain you. All x86 processors, all the Intel processors which are available, these are CISC processors. And all the processors which are used in the mobile phone, these are called as microcontrollers. These are called as microcontrollers. These are RISC processor. For example, I don't know whether you heard about ARM processor, ARM processor, the present ARM processor. This ARM processor architecture is based on the RISC processor and CISC processor. Now you know what is RISC processor, which is RISC processor and which is CISC processor, right? I told you Intel, all your laptop processors which are all RISC in nature, and all other processors are RISC in nature, whichever we use in the mobile phones, which is called as ARM. Okay? Now what is this? What is CISC, what is RISC? See, now this classification is done based on how easily you write a program for these processors. Okay, listen carefully. I will write a simple program here. I will write a simple program here to multiply two numbers. To multiply two numbers. Okay. To multiply two numbers. Listen carefully here. You have a processor. Where your variable ABC, the variable ABC are memory variables. So these are memory, okay? You have a microprocessor where you have the variables which operands or variables which you call it as is available in the memory, okay? And this one is part of your microprocessor. I told you in the beginning that microprocessor has registers and arithmetic logic inside that. Your memory is outside the microprocessor. Okay? Now, assume that you have to multiply two numbers which are available in the memory locations, right? It's in the memory locations. And you all know that these memory locations exist outside the microprocessor, right? But multiplication happens in the microprocessor, right? So, in the CISC processor, listen carefully, in the CISC processor, just write one instruction, say multiply, this is assembly instruction for multiply, mul, A, B. Just mention these two memory locations. That's all. Right? It will multiply the content of AB. Understood this? This one instruction is enough to do for complex instruction set computing. You can see this one instruction in CISC processor internally breaks into multiple instructions. What are those multiple instructions? To break it down, to fetch the data from memory to microprocessor. See, this is your microprocessor. This is memory. Suppose if microprocessor wants to multiply these two memory variable, it has to fetch it. Right? It has to fetch A, it has to fetch B, multiply A and B and store it in A once again. But do you need to write those instructions? No. Just one instruction is enough. But remember, microprocessor internally does remaining things. It takes time. Microprocessor internally does those things. Instruction looks simple, but it does complex operation inside. Have you understood this? This one instruction not only multiplies the content of the memory location A and B, also internally it does the fetching operation, the fetching work. You don't see that. I've understood this. Okay? Any microprocessor which is designed to have such an easy instruction, right? While executing, it will be break into micro instructions. Such microprocessors are called as complex instruction set computing. Instructions may look very easy here, only one instruction. You just have to write only one line program, just one line program, enough. But that one line program does so many other things inside, you don't see that. It takes time for that. It takes cycles, many cycles for that. Such computers are called as complex instruction set computing. Now, let us go to the other part, which is called as reduced instruction set computing, RISC. RISC. Here, suppose if you want to do this operation, multiplication of A and B, it is not possible to do it with one instruction. You have to do 4 instructions instead. 4 instructions instead. Right? So you have to write one instruction to get the data from memory, put it in one register, get the another data from memory, put it in another register, then multiply within the register, okay, and then store it back. Right? But here, one instruction is enough. But remember one thing here, this also does the same thing which this is doing. This instruction also does the same thing, what RISC is doing. Both are doing the same thing. This also multiplies A and B, this also multiplies A and B. This also has to take this A to the register, B to the register, and then multiply, put it back to the memory. Right? See, one thing you remember, any processing which is going to happen in microprocessor, its operands has to be available, operands have to be available in the register only. That's very important. Internally, it executes from the registers only. But in CISC architecture, only one instruction you are writing. Multiply A and B. A and B are memory locations. But this one instruction internally fetches A to one register, B to another register, multiplies those two registers, stores the result back to the register A. But it is not shown here, right? It's not shown here. But this one instruction does all those operations. Have you understood what I am trying to tell you? That's why this is called complex instruction set. Instruction is only one, but complexity is huge out of that. But in RISC, it's different. You need to write 4 instructions separately. That's why it's called reduced instruction set. Instruction may be in 4 lines, but one instruction does only one work. It will load A, you need to write this program. It will load data A from register 0, it will load data B to register R1, multiply R0, R1, it will multiply registers R0, R1 because this instruction, multiply instruction, microprocessor can take only data from registers. Then store the result, whatever is stored in R1, this multiplies R0, R1, stores the result back to R0. Then where your product is in R0, store it back to A. Now how beautiful it is. There is only one instruction does same thing, same operation. There are 4 instructions does same operation. Right. Now question comes, which is better, which is not, it's not better. Huh? Why this is better? That is what called programming easiness, right? Programming easiness. For programming easiness, this is good, right? Who will write 4-line code? Writing one line code and getting the things done is better, right? But in terms of speed, this is not good. Why? because it has to do some background work by itself, right? The speed of execution is not good here. But here, speed of execution is good. Why? Because there is only one instruction. It need not do anything else. Have you understood this? That is the difference between your CISC processor, RISC processor. For real-time operations, for example, your Raspberry Pi, I don't know how many of you know about Raspberry Pi, all this Internet of Things, IoT devices, because their real-time is very important. Real-time is very important, right? Wherever the real-time operations are required, okay, then you go for this. Your speed is a concern over there. Wherever you don't do real-time operations, for example, training your network, all those things, okay, you go for this. That's the difference between RISC and CISC processor, okay. Both the things you're going to study. Where? Which course? This you're going to study here now. The other one you're going to study next year. In which course? Computer architecture. Right? Okay. So all your Intel processors, 8086, 80x86. 8086 is one, x86 because it's all future evolutions will be taken care by that X value. It is RISC processor. This is very important for you to know, okay? Okay, now I will directly go to the architecture, what is there inside our 8086 microprocessor, okay? This is very interesting one. I'll just show you this. You need to remember this. I'll directly go inside what is there in the 8086. Okay. Okay, let's just, so what you see here is a 8086 microprocessor based computer. It's a very old one, okay. During, I think you know, you might not have born during this time, okay. Still we are having these kits in our college, but we are not giving you the kits, okay. Because you yourself feel that, okay, why we need to study such a old kits. This is where you are supposed to do programming. But I am sure if I give this to you, you will never like this microprocessor at all. That's why we are not giving you this, okay. So this is your 8086 microprocessor chip, okay. And what you see here is 8086 based computer. The first computer, which is called as XT computer. I don't know how many of you remember that, okay. It's all the same thing, right. So it has a keyboard. See, this is the microprocessor kit. It has a keyboard. Do you think that you do the programming, such a big programming, just by entering its hexadecimal code, right? Just or assembly code like this? If I give this kit to you, you will have to write the program just by using this. Your programming will not be so easy as you do it today in the class. Today what you do in the class, just open a text editor, go and type the program, then only three commands, in turbo debugger you see the output, right? But this is not like that. You need to write the address also. Everything you need to write. The programming using this kit is not so easy as you do it today. But this is the reality. This is the reality of these microprocessor kits, microprocessors. This is a 8086 based microprocessor. You have 8086 and you have corresponding memory also. I said memory is external, and also there are some control circuits, right? Okay. So just to show you, I have put this. this is actually the basic architecture or model of your 8086 microprocessor. This you need to take an imprint on your mind, on your brain. I don't know whether you have mind or not, but brain is there, right? Okay? Mind is different, brain is different, okay? This is what you're going to study. This is your 8086 microprocessor. Now, first thing to know what it consists of, okay? What it consists of. And I told you since my first class that microprocessor are nothing but a set of digital circuits. What are those digital circuits? What is that something you studied in your digital design? Same thing. You studied registers, you studied flip-flops, you studied D flip-flop. Using D flip-flop, you all know how to construct 4-bit register, general purpose register. Just extend it to 16-bit, that's all, you get 16-bit registers. Same register is there in the microprocessor, many, not one, many. The purpose of this register is to store the data, 16-bit data, as per our requirements. Hope you are understanding this, right? Now, and then you need to remember what are the registers present. Suppose if I ask you, our country India, what are the states of India? You know, right? You can name it, right? You all know, right? Being an Indian, we all know it. Or maybe whole world, suppose you go to US, what are the states of US also, you know it, right? So like that you remember here, what are the registers it consists of? First, I will talk about general purpose register. I will go and tell you all these things now. First, there is a general purpose register. Okay. Now, there are 4 registers. All these are 16-bit registers. Okay. 16-bit registers. 8086 microprocessor has 16-bit register. Okay. All are 16-bit register. Okay. Now, I will come one by one. When I said register is 16-bit, what about the size of the ALU? 16-bit only, you know it. Now, see, these 4 registers, okay, these 4 registers are 16-bit registers. These 4 registers are 16-bit registers. 4 16-bit registers. 4 16-bit registers. Okay? And these are called as general purpose register. And there are, these are given names, AX, BX, CX and DX. What is the meaning of general purpose actually? What is that something which is a general purpose? It can be used for anything, right? Anything, right? So, as the name itself indicates, you can put any data. It is flexible to you to use. You are free to use these 4 registers. And one more thing you remember, these general purpose registers can also used like a 2 8-bit separate registers. Suppose if there is a requirement of working with 8-bit data, where are the registers available? Half of that you can use. Come on, hope you are understanding. Your 16-bit register, right? Half of that you can use. Right. Now you see, if I put these two separately, right, 2 person has to sit separately, right? Suppose if I have a bench where you can put, not a 2 chair, 1 bench, 1 person also can sit, right? 2 person also can sit. That means that can be used either by 1 person or by 2 person. Similar way, this 16-bit register, if you want to use it as a 2 registers for your 2 data, 2 8-bit data, you can use it separately. Have you understood this? You can use it separately. That's why these general purpose registers can be used in flexible. Understood this? Okay. Now, there is one more register called stack pointer. Stack pointer. This is also a 16-bit register which is used to keep the pointer to the data. Similarly, you have base pointer. This is also used for stack operation. Source index, destination index. Source index, destination index is used in arrays. In arrays, you use these indexes extensively, right? Right? Source index and destination index are used for the arrays. All these are registers only. Similarly, you have this another set of registers which is called as code segment register. I will come back to this, don't worry. When I talk about memory segmentation, you have stack segment register, data segment register, extra segment register, instruction pointer. All these are special purpose registers. Once again, all these are 16-bit registers only, and these are used for special purposes, for its own purposes. We'll come back to the one by one those purposes. Right? Now, see, there is one more ALU here. This is for address generation. I will come back to this. Why we need this ALU for generating an address. I will come to that memory segmentation. Okay? Then, as far as possible, ALU, you know what is ALU? It performs arithmetic and logic unit. Now, see here, there are two more registers here. One is for the operands, another one is called flag register. This flag register is very important. What this flag register has? These registers have some flags. These individual bits of these registers indicates whether carry is generated or not, whether result is 0 or not, whether your data is parity or not, whether there is an overflow or not. These individual bits of the flag register is going to indicate that. We will come back to that, don't worry, we will come back to that. One by one you are going to see this register separately. Okay? Now, this is a control unit. These are the logical circuits to control all these things. And say this is called as prefetch queue. What is prefetch queue? I will tell you through next slides. What is this? See, the instructions are fetched from the memory. Okay? Whenever microprocessor needs to do an execution of an instruction, instruction has to be fetched from the memory, right? So, what microprocessor does is, it has got something called instruction 6-byte instruction fetch queue, right? So, it will not only fetch the present instruction, along with that it can also fetch the next instruction and keep it in the queue. What is the purpose of having a queue here? So that if you can reduce time by prefetching the instruction and keeping it in the prefetch register. This also register. It will prefetch the instruction and keep. I will explain you this. I have some more slides. Okay? Maybe next class I may go for that. Okay? Now, you understood what your microprocessor consists of now. Now, can you tell me what ultimately it has, which you studied in DD? ALU and registers. See, you can see this microprocessor is nothing but full set of registers only, yes or no? See, these are your registers which you studied in your DD. These are registers studied in your DD. Is the register studied in your DD? Register studied in your DD. You have this arithmetic and logic. This is arithmetic unit. Some adder. What is the arithmetic unit? Your adder subtractor, come on, which you studied in your digital design. Right? Okay? That's all, nothing else. This is what your 8086 microprocessor is. Why I am telling you to just have its imprint in your brain so that you never forget what your microprocessor, 8086 microprocessor consists of. Never forget this. Okay? So, we will stop today's class.